Hello everyone, now we talk about the paper with the title RFNet-4D, Joint Object Reconstruction and Flow Estimation from the 4D point clouds. We see the joint work with Duc-Thanh, Nguyen, Binh-Son, Quang-Hieu, Pham, and Sai-Kit. So let's start with the first part, Introduction. Object reconstruction from 3D point clouds had achieved impressive progress in the computer vision and computer graphics research field. However, reconstruction from time-varying point clouds, a.k.a. 4D point clouds, is generally overlooked. Literature has shown several breakthroughs in deep learning for reconstruction of 3D models from point clouds. Recently, the research community has seen great successes in neural representations using implicit fields. The first work on this field is occupancy flow. They extend the deep implicit representation from the paper occupancy network into the 4D space. The latest work is LPDCnet, which parallelly established the dense correspondence at a different time step, and explicitly learning continuous displacement vector fields. However, this work still has many drawbacks, and exists many challenges to solve, such as ignore aggregation of the set properties from multiple frames, inefficiently capture the temporal dynamics, low computational efficiency due to solving narrow ordinary differential equations, require large amount of annotated data for supervision chaining. From the above challenge, we propose RFNet-4D to solve this problem. Our network takes as input a sequence of sparse, incomplete, and noisy 3D point clouds and simultaneously reconstruct a sequence of occupancy maps and estimate a sequence of vector fields. Our network is an end-to-end architecture that is able to perform both 3D reconstruction and flow estimation. Our network structure can model temporal flows in 3D point clouds using unsupervised learning with fast processing time in both chaining and inference. Our compositional encoder includes a temporal encoder and a spatial encoder. Inspired by occupancy flow and LPDC, we adopt the parallel Raslet variant of PointNet for both spatial and temporal encoder. These encoders are basically similar in their architectures. The only difference is that the spatial encoder rotates one point cloud PT at a time, while the temporal encoder acquires the whole point cloud sequence. The joint decoder takes a spatial temporal representation ET and the original point cloud sequence as input, then passes this input into two decoders to perform flow estimation and object reconstruction. Our RFNet-4D is changed by joining performing two optimization processes, unsupervision for flow estimation and supervision for object reconstruction. Let's move to the next section, experiments. Here is the qualitative results of our proposed method from a sequence of sparse point clouds. Comparing with other methods, our method can capture convincing motions and correspondences across time, whether ONet-4D and PSGN-4D are not. Moreover, by coupling both spatial and temporal information aggregation, our method achieves better geometry recovery than 4DCR or flow and LPDC. The result also show that our method is better than existing works, for example, our flow LPDC in flow estimation. As shown in the table here, our method achieves higher robustness on non-uniform sequences with large variations in both seen and unseen individuals. Our performance is significantly better, but still be comparable, because our flow estimation model would change it by unsupervised fashion, unlike other methods. Especially for the unseen individuals dataset, our method achieves state-of-the-art performance, showing its robustness to novel object sets. We also conducted several ablation studies to verify different aspects in design of our model. Note that in each ablation study, only one chain was applied at a time, while other settings remain unchanged. Despite our model has larger chaining memory footprint, our method is faster in both chaining and inference. Lastly, let's summarize the key idea. In conclusion, we designed 4D reconstruction method that simultaneously performs flow estimation and reconstruction across time. The experiment result demonstrated our method advanced in comparison to state-of-the-art on a challenging dataset, as well as the effectiveness of the joint learning approach. Despite the fact that our method achieves state-of-the-art performance, it still has many drawbacks to improve. Firstly, we can improve the low accuracy of unsupervised flow estimation. We can extend the experiment on the different types of objects, and we can extend the pilot to fully unsupervised for both reconstruction and flow estimation. Thank you for your attention.